This lesson is about motion under gravity. We are going to consider a situation where the object is projected vertically upwards from a point, and then it comes back to the point of projection. So by the end of the lesson, you should be able to do the following. You should be able to describe how the velocity of an object changes from when it is projected to the time it comes back to the thrower's hand, that is when it comes back to the point of projection. You should be able to describe forces acting on the ball before projection and after projection. You should be able to determine the maximum height covered by the object. Number 4, you should be able to determine the total displacement of the object. Number 5, determine the total distance covered by the object. And number 6, you should be able to determine the area under the graph and compare it to the displacement of the object. So let's go straight to the first simulation. In this simulation, we are going to imagine we are throwing an object vertically upwards. So I've put the simulation in slow motion. So that is what happens. We are going to repeat this simulation several times so that we can discuss the forces which are acting on the object before it is projected in the course of its motion from this point to maximum height and back to the hand. And of course, we are going to try and draw a graph. For example, how will a velocity time graph for this motion look like when it is projected from this point? Of course, the object is in contact with the hand. So it is the hand which pushes it upwards, then releases it at that point, rises to maximum height, and then falls back to the hand. How does its velocity change? That is what we are going to draw in this space here. The object is released with a velocity of 30 meters per second. And then when it comes back to the hand with a velocity of 30 meters per second, but in the opposite direction. And this is how the velocity time graph looks like. So the object is projected vertically upwards with a velocity of 30 meters per second, vertically upwards. So when t is 0, the object has a velocity of 30 meters per second vertically upwards. Of course, we are going to take vertical motion as positive. That is why these values are positive. And you will agree with me, as it moves upwards, its velocity decreases with time. So it is released with 30 meters per second. After maybe 1 second, its velocity is 20 meters per second. After another 1 second, that is the second, its velocity is 10 meters per second. And at the third second, its velocity is 0. And that is exactly what happens at maximum height. At maximum height, the object is momentarily at rest. Let's repeat this simulation so that we can see this clearly. Released at 30, it is momentarily at rest and then accelerates downwards, where it comes and hits the same position with a velocity of 30 meters per second in the opposite direction. Let's repeat that one again. Released with 30, reaches 0, comes back to the thrower's hand with a speed of 30 meters per second vertically downwards. And you can see that is true. It is released with a velocity of 30 meters per second vertically upwards, reaches maximum where its velocity is 0. It reaches maximum height after 3 seconds, and then it starts moving downwards, and its velocity increases downwards back to the thrower's hand, and it comes back to the thrower's hand with the same velocity with which it was thrown. In terms of magnitude, of course, the directions are different. You can see that motion downwards, the velocities have negative values. And you'll see that from maximum height, the velocity is increasing again at a rate of 10 meters per second every second. So it changes from 0 meters per second to 10 meters per second after 1 second, that is when it is moving downwards, to 20 meters per second, and finally 30 meters per second. So this one is very, very important. There is one feature which I'd like you to be very careful about. When students look at this graph, they always think that when the object is up here, this is when the object is at maximum height. Just because the graph looks as if this is some kind of height, don't get confused by that. Just consider the velocity that the object has at the point of projection. Just ask yourself, with what velocity is the object projected vertically upwards? Because unlike a situation whereby the object is released from some height and then it falls with increasing velocity, in this situation, it must be thrown. That is why there is this hand here. You must throw the object. And in a moment, we are going to look at the forces which are acting on the object, which is, of course, exerted by the hand. So, be very careful when you're describing this. Let's look at the next simulation. Over here, now we've got a detailed analysis of this motion. The object starts from point B. This is where we start our timing. We don't consider the situation whereby the hand is in contact with the object. The hand is in contact with the object so as to accelerate it upwards. But as soon as the object leaves the thrower's hand, that is when we start timing. And it leaves the thrower's hand with a speed of 30 meters per second vertically upwards. So the hand is there to accelerate the object. And then as soon as the object leaves the hand, it has enough momentum to keep it moving vertically upwards. So the object starts from point B, rises to point C, and falls back to point B. Starts at point B, rises to point C at maximum height, and then falls back to point B. Let's see whether that is the situation. Starts at point B, rises to point C, and falls back to point B. It's exactly what we have discussed before, and we have already looked at how this graph comes about. Now let's consider the forces which are acting on the object. Before we start pushing the object upwards, this is the object, it is an apple. Its own weight acts vertically downwards. The hand is supporting the apple, so the hand must be exerting a force vertically upwards in order to support the apple. So in this particular situation, the weight of the apple is equal to the amount of force that the hand is exerting upwards. That is why the apple is in a state of equilibrium. The upward force is equal to the downward force. You can talk about the reaction. The reaction is equal to the action. That is Newton's third law of motion. And it's very simple to understand it. When a system is in equilibrium, it always means that the resultant force on the object is zero. That means opposite forces are equal. So the amount of force that the hand exerts on the apple is equal to the weight of the apple, and that is why the apple remains in a state of equilibrium. Now, as soon as we apply a force, you can see that we have just started applying a force vertically upwards, then the amount of force exerted by the hand is greater than the weight of the apple. And that is why this apple starts to accelerate upwards. This one is very, very important. Remember, we are considering the forces which are acting on the apple. In our previous situation, we saw that the two forces were equal in magnitude and opposite in direction, and that is why the apple was in a state of equilibrium. In this new situation, as soon as we start pushing the object upwards, we must apply a force which is greater than the weight, and that is why this apple starts to accelerate. It means there is a resultant force on the apple. That resultant force is the one which makes the apple to accelerate upwards. And because there is a resultant force, this force exerted by the hand must be greater than the weight. Let's see what happens to that force as the object moves. So, let's move the object. Do you see what has happened? Let's repeat the simulation again. I want you to concentrate on the forces only. For the moment, do not concentrate on the distances which the object rises and falls. Just concentrate on the two forces, this force and this force. And here we go. We observe several situations. 1. As we push this object from this point to this point, before the hand leaves contact with the apple, there is the force exerted by the hand and the weight of the apple. Those two forces exist. They are being exerted on the apple. And because this force is greater than this, the apple accelerates upwards. As soon as the apple leaves the hand, the force that the hand was applying on the apple disappears. Again, let's see that. You can see that force has disappeared. It's only the weight which is remaining. Let's repeat it again because I want you to concentrate on this force and the fact that it disappears and then comes back when the apple makes contact with the hand once again. The other thing you notice is that the weight of the apple is there throughout the motion. So here we go again. That force disappears, the weight remains, comes back, and the force reappears again. But this time, it reappears and it is equal to the weight of the apple, because it is like when we started initially, when the apple was not being moved. The two forces were equal in magnitude but opposite in direction. Now, for the sake of understanding, I'll repeat it again. Now, one other thing, notice the length of the force which is applied by the hand on the apple is not the same as the length of the force which is applied by the hand on the apple when the apple is not in motion. So here we go. That force disappears, the weight still remains, it comes back here, and the force reappears, but it's got a lower magnitude than when the apple was being accelerated upwards. Now notice that the weight remains, the weight is throughout the motion. It always points vertically downwards. This weight of the apple, it is the one which is making the apple to decelerate as it rises from this point to this point. We repeat that because I want to explain that point. Notice that as soon as the hand is no longer in contact with the apple, the only force acting on the apple is its own weight. And its own weight is opposing the motion of the apple. The apple is moving upwards, but the force is acting downwards. But when the apple is moving downwards, the weight is also acting downwards, and that is why the apple accelerates downwards. So in this motion, the apple accelerates because the weight is acting downwards. It helps to accelerate the apple downwards. But when the apple was moving upwards, the weight was acting downwards. So because the weight is trying to oppose the motion of the apple, it decelerates the apple. So the apple slows down and comes to rest momentarily at this point, and it is also this point. After 3 seconds, it reaches maximum height, and that is when it is momentarily at rest. So over here, it is slowing down. And indeed, you can see these values, they agree. It starts with 30 meters per second as soon as it leaves contact with the hand at that particular point. And then after 1 second, it has reduced to 20 meters per second. After another 1 second, it has reduced to 10 meters per second. And after another 1 second, its speed has become 0. So the rate at which the velocity is reducing is 10 meters per second. This is the deceleration of the object. The deceleration is 10 meters per second squared. And indeed, that is the value of the acceleration due to gravity. The reason why it's got a negative value, the acceleration has a negative value, is because we are considering motion upwards as being positive, but the acceleration due to gravity is always downwards. The next point I want us to consider is the amount of displacement of the object. You will agree with me that the amount of displacement vertically upwards is equal to the amount of displacement vertically downwards. So if this rises through maybe 9 meters, it will fall through the same 9 meters. That is why this yellow line is equal to this yellow line. In magnitude, the amount of distance covered by the object as it rises is equal to the amount of distance covered when it falls back to the thrower's hand. So it starts from this point and comes back to the same point. We have already looked at the concept of displacement, and here you will agree with me that the displacement of the object is 0. We have also talked about the significance of the area under a velocity time graph. For example, this area here is supposed to represent the displacement of the object from the thrower's hand to the maximum height, the whole of this triangle. The next triangle, which is here, this triangle, represents the amount of displacement from maximum height back to the thrower's hand. The two, you can see if I work out this area, I'll get a positive value. I'll get a positive value of 45 meters. When I work out this area, I'll get a negative value of 45 meters. So this displacement is positive and it's got a magnitude of 45 meters. This displacement is negative and it's got a magnitude of 45 meters. When you add these two values, you will get 0. That one is very, very important. And indeed, we have seen that the displacement of the apple is 0 because it starts from this point, rises to maximum height, and then comes back to the point from where it was projected. So indeed, that is proof that the displacement of the apple is 0. Because we can see from this diagram, we can reason out, since it comes back to the point of projection, displacement, the total displacement must be 0. From the graph, if we work out this area, it is equal to this area in magnitude, but one area is positive, the other one is negative. When we add the two in order to get the total displacement, we are going to get 0. That one is very, very important. The other aspect is this. We know that the gradient of a velocity time graph represents acceleration. If we work out the gradient of this line here, it's like dividing 30 divided by 3 and we'll get minus 10 meters per second squared. That is when it is moving upwards. At the point, at the maximum height, this point, many students usually think because the object is at rest, it is not accelerating. That is not true. If you want to prove that it is accelerating, find the gradient at this point. You'll find that you will draw your right-angled triangle somewhere around here, and you'll find that that gradient will again have a value of negative 10 meters per second squared. So, when the object is moving upwards, its acceleration is minus 10 meters per second squared. At maximum height, its acceleration is minus 10 meters per second squared. Now, on its way downwards, if you calculate this gradient, you will again find that it has a negative value. So, this object has got uniform acceleration throughout. Don't get confused by this. Many students think because this motion is upwards and the next one is downwards, they think that this must be negative acceleration, this must be positive acceleration. No. We define our acceleration depending on which direction we took as positive. So if we take upwards motion as positive, then the acceleration will have a negative value. And the whole of that, whether it is moving upwards at maximum height or moving downwards, the acceleration is going to be equal to minus 10 meters per second squared. Those are very important points. Let's stop this lesson at this point so that you can have time to look at the video deconstruction document where I've given you step-by-step questions discussing everything that we've discussed in this particular video. So go straight to your VDD and attempt those questions. Remember to enroll in my online class for free step-by-step tutorials, revision notes, and video deconstruction documents which will help you to understand my video lessons. Feel free to invite your friends so that we can form a wider discussion group.